So now I'm going to go over how to use the Analog Discovery 2 as an oscilloscope. In the waveform software, select the scope workspace, and you're presented with a typical oscilloscope screen just like we have in the lab. In the center is your main display. Over on the far right are your channels, channel 1 and channel 2, which are shown on the pinout diagram as scope channel 1 and scope channel 2 respectively. This is also where you can change the scale of your axes and any offsets. So that could be done separately for channel 1 and channel 2, and then the horizontal axis time is changed slightly above that. So I have my Analog Discovery 2 configured such that channel 1 is hooked up to a DC input, outputting at 1 volt. So that is scope channel 1 positive is connected to my 1 volt DC input. Scope channel 1 negative is connected to ground. So what we can do, we can enable those outputs and then enable the scope. And we see a horizontal line at 1 volt. This makes sense because since we're just outputting a DC output, there should be no change in the signal over time, which is what we see. And since the output is at 1 volt, we see a 1 volt output here. I've set up my channel 2 to be a 1 kilohertz sine wave with an amplitude of 1 volt. So if I enable scope channel 2, I see a sine wave that changes with time. The overall voltage value changes with time. And we see peaks at 1 volt and minus 1 volt, since the amplitude of this wave is 1 volt. The overall peak-to-peak difference is 2 volts. Now you'll notice that the signal is jittering around quite a bit. This is because the trigger settings are not set up properly in this case. So since my voltage input that changes with time is on channel 2, what I can do is up at the top, there's this source option, and right now that's set to channel 1. If I change that to channel 2, the osciloscope's going to sync its update rate with the output from channel 2, and now the screen doesn't jitter back and forth. I can enable channel 1, and since that is a constant 1 volt signal, that doesn't move around anyway. So in this case, we got pretty lucky with our scale on both channel 1 and channel 2. We can see both signals, and we can see the entirety of both signals. And there's not really any question about which one is which. However, if the settings were not set properly, or if our voltage source was not perfectly defined to be 1 volt in amplitude or 1 volt DC, this screen might look a little bit different, and you might not be able to tell very much about what was going on. For example, if the channel 2 range was instead of 500 millivolts per division, but 5 volts per division, we lose a lot of resolution on our overall signal display. And since a lot of the calculations are done using the values on this display, we get these jitters again because the Analog Discovery 2 can no longer determine what that update rate is and where to trigger updates. So what we can do is we change our range such that the signal covers the entirety of the screen. So if we put it to 1 millivolt per division, it's obvious that we've gone way too far. The signal clips at the top and the bottom of the screen. Instead, we can try 50 millivolts per division, still too far, 100, still too far, and 200, very close, but still maybe are missing some of the signal at the top and lower end. But if we go 500, it doesn't quite go to the top. So instead, let's just type in 350, and that's a little bit better. Oops, 250. Great. The other thing you can do is change the offset. This works as you would expect, except it's typically in reverse when you're changing the offset for your channels. So I'm going to put this at 500 milliseconds per division, just so we can see what the offset does. If we change the offset to 1 volt, The center of our display is now at -1 volt. So the channel 2 input shifted upwards. If we go to -1 volt, the center of our display will be at +1. So we shifted downwards. The offset for channel 1 and channel 2 can both be different. So in this case, we've set our channel 1 offset to 0 volts, and we see over here highlighted in yellow the scale for channel 1. If we flip over to channel 2, that's going to switch the scale on the far left side. Now it's highlighted in blue, just like channel 2 is, and we see that our 0 is now here. Note that do definitely be careful with what your scales are set to, because in this case, if you weren't paying close attention, it might look like your channel 1 input was actually a 2-volt source, because that's what the offset settings for our channel 2 kind of make it appear. But in actuality, it is only 1 volts, just like before. So once again, I'm looking just at channel 2, and I have my sine wave input. Now, I could count all of these peaks to determine what the frequency was. I could use the scale to determine the overall peak-to-peak voltage. But if we had a more complicated signal, that might be really difficult. So we can use some of the measurement functions on the oscilloscope in order to get some of this information for us. So up near the top, we can just open up the measurements tab, and that'll give us this extra window pane on the side that'll allow us to add measurements. In this case, I'm going to hit Add Defined Measurement, and since my signal is on channel 2, I'm going to select channel 2, vertical, and let's get the maximum voltage, the minimum voltage, the average voltage, and the peak-to-peak voltage. Next, we'll look on the horizontal axis and get the frequency of our signal. Once we've added all of those, we can close this, and we see the value of these measurements in the window pane, in the measurements pane. So we see our maximum voltage is 1 volt, minimum voltage is -1 volt. Intuitively, this makes the average 0 volts, which is about what we're seeing. Peak to peak is at 2 volts, which is exactly what we expect. And the frequency here is showing 1 kilohertz or 1000 hertz. If I change the frequency of my input from 1 kilohertz to something like 2 kilohertz, we'll see over here, obviously our sine wave has gotten a lot more compressed, and we see the frequency here is 2 kilohertz. Now, it can be a little bit hard to interpret signals when it's this compressed, so just like with our voltage offsets and range, we can change our time offsets and range. In this case, let's change from 2 milliseconds per division to something like 5 milliseconds per division. That made it worse. We'll go the other direction and instead do 200 microseconds, and now it's a lot wider. Now note that just like the accuracy of these measurements might change depending on the scale of your window for your voltages, it can also change for the overall horizontal width or time width of your signal as well. So whereas before we have a solid 2 kilohertz, if we reduce the voltage division extremely small, say 100 nanoseconds, now the AD2 can't interpret what the frequency is whatsoever. Additionally, our voltage input looks like a single line when we know that that is in fact not the case. So we would have to change our time divisions in order to better visualize the data. This is better, but still not good enough for our frequency measurement to tell us what we want. And since it doesn't capture the whole range of voltage, our voltage measurements are also incorrect. So we'll go back to 200 microseconds per division on the time axis, and we have correct frequency value now. Just to demonstrate how the precision of the voltage measurements also change based on our range settings, I'll make the range something like 5 volts per division, and now we see that we're at the average voltage is closer to 11 or 12 millivolts, whereas when we had it at the proper spacing, the average is much, much closer to 0, indicating that a much more precise measurement.